So another topic that's covered in section 5.4 is this net change theorem. So previously, for the fundamental theorem of calculus, this integrand here was written as f, okay, and where we had an antiderivative, capital F, right? But since capital F is an antiderivative of f, we can write this equation here from that fundamental theorem of calculus. That is, that we replace that integrand f with f prime, this is still the same thing, okay? And so this integral here actually gives us a net change of cap f, which is the antiderivative. And so this is the net change theorem. And so the typical example is when we have a position function for some particle, okay? And so for, let's say we have a position function for some particle, or let's say we have the velocity of some particle, and we want to compute, I mean, there's two things that we can compute related to this particle moving. One is displacement, okay? And the other is an actual total distance traveled. Because it turns out that displacement does not actually give us a total distance traveled, in the sense that when particles are moving to the right, that distance is considered positive. But when a particle is moving to the left, that distance is considered negative. Okay? So displacement will only give us a displacement, so a change in position, a net change in position. Okay, but it does not give us a total distance traveled. Okay? So these two things are computed by the following. If we have velocity of a particle, of course, velocity is derivative of position. So we would integrate if we want to compute displacement between time t equals a and t equals b, displacement would be given by this interval. We would integrate from a to b, v of t dt. Okay, where v is velocity. And of course, like as I said, v is s prime of t. For total displacement traveled between time t equals a and t equals b is related, but what we have to do with the velocity function is we have to take the absolute value. So now the absolute value, taking the absolute value will give us, so that if the particle is moving to the left, that distance is considered positive. Okay. So note the difference between these two. So as an example, find these for a particle moving with velocity given by t squared minus t minus 6 we'll do this for time between 1 and 4. So we'll compute both of these things, all right? For computing displacement, so as I said, this is really equal to integral from a to b of s prime of t dt. Okay, and of course, if we integrate this, okay, we are going to use fundamental theorem of calculus and simply compute s of b minus s of a. Okay, that would be a displacement, and it's the s is the position function. Here, though, we can't simply write this. We have to, whenever we have the absolute value, we have to deal with that separately, and we'll get to that. But for now, let's compute displacement. So for this displacement, we are computing integral from 1 to 4 of t squared minus t minus 6 dt. And so this equals, we find the antiderivative. So the antiderivative is 1/3 t cubed minus 1/2 t squared minus 6t. I set myself up to use fundamental theorem of calculus. So I put 1 there and 4 there, and so this equals. So I first plug in 4 into that expression. So it would be 1/3 4 cubed minus a 1/2 4 squared minus 6 times 4. And then minus, and I can put this in square brackets if I'd like, when I need to, but I'll do it. And then now I plug 1 into this expression. So this will be 1/3 1 cubed minus a 1/2 1 cubed minus a 6 times 1. Put that in square brackets. And so here we evaluate. And so if you do this evaluation, I believe we end up getting minus 9/2. Okay, and so we would conclude here that the particle has moved to the left because of the negative sign. Okay. Now for total distance. All right, so now we integrate the absolute value of v of t. So what we need to do is we need to take a closer look at the velocity function and when it's positive and when it's negative. Okay, so we have our velocity functions t squared minus t minus 6. And so we need to plot this. And we need to try to plot it quickly. And so what I'm going to do is I'm going to set this equal to 0 and find roots. Okay, because that's going to help us plot the function. And we'll also need those roots to see when there's a sign change. So here I can factor t minus 3, t plus 2. I believe this works. So we have 3 and minus 2 as the roots. And the one that's important here is t equals 3, which is in our interval from 1 to 4. Okay, so what these roots tell us is that if we were to plot this function, so we have a root here at minus 2, a root here at 3, and I know this is concave up. I mean, it's positive coefficient from the t squared, that s of t is going to look something like this. Okay, so between 1 and 3, v of t is negative. Okay, but between 3 and 4, v of t is positive. So the way to construct my integral, we would want to integrate. So we would set up an interval from 1 to 4, absolute value of v of t dt, and this would equal, we would write this as 2 intervals. Okay, we would write this as an integral from 1 to 3, the negative v of t, because we want this to actually be positive, and so what we do is we negate v of t. Okay, I mean, we're basically taking the negative of something that is negative, making it positive. All right, so this would be an interval from 1 to 3. If I negate this function here, I would get a minus t squared plus t plus 6 dt. And then I would add to that, and then I would integrate from 3 to 4, v of t just as it is. T squared minus t minus 6 dt. And I mean, here we find the antiderivatives. Of course, this antiderivative for this second integral would be the same as for our displacement. This antiderivative for the first term in this total distance would be, of course, the negative antiderivative. I'll let you go through the details to show that the total distance traveled is going to be 61/6 if you add up the total of those two definite intervals.